All right, hello and welcome back. So this is another ALEKS topic, and this is a requested topic, so thank you very much for the request. If you've got other requests, feel free to comment below, and I will get to them sort of as soon as I can. Really depends on my schedule, but usually the turnaround's pretty quick. So this is a great topic. It's definitely very challenging. The title is Using Reaction-Free Energy to Predict Equilibrium Composition. So we're going to basically be using this delta G information, this reaction-free energy, to figure out some information about the equilibrium. So the first thing when I was looking at this topic, the first thing that really jumped out at me is that there's a relationship between delta G and K, the equilibrium constant. And that relationship is delta G equals minus RT natural log of K. And that's something that jumped out at me, obviously, because I'm an instructor and I know how to do this stuff. But I think by reading that title, we know that reaction-free energy is this delta G, and equilibrium, that's going to be related to the K value, the equilibrium constant for your equilibrium. And this is just a nice relationship between those two things. And they're really going to tell us similar things. So this is a positive value, positive 41 kilojoules. And that tells us some information about, where do we expect this equilibrium to lie? That will be related to the K value, the equilibrium constant for that reaction as well. But we'll get into more of that as we go forward. So I've just rewritten this equilibrium down here just to give me a little bit more space to work. But I'm going to go ahead and fill in this information now. So we've got a reaction vessel. We're going to put in 2.61 atmospheres of our NaCl, and then 1.83 atmospheres of our nitrogen monoxide. That means we're going to have 0 atmospheres of our Cl2. And this is really an important thing to sort of recognize, is that our Cl2 initially has 0 atmospheres, has 0, pressure. So to get to equilibrium, we have to shift to the right. So, anytime we see a 0 on either side, that tells you right away that our change line should be minus 2x, plus 2x, and plus x, indicating that we're shifting to the right. Now, we don't need to do a full ice table for this problem, but we do need to sort of recognize which way is it going to shift to get to equilibrium. That's really sort of how we're going to answer these first two questions. So figuring out, which direction the reaction is going to shift by shifting towards the 0, that's probably the best way to think about it. So now that we know that this reaction is going to shift to the right, so maybe we'll put that in parentheses here, shift to the right in order to get to equilibrium, then we know that the concentration or the pressure of NO and Cl2 should both increase as I let this reaction go to equilibrium. We're going to convert some of these reactants into products because I've got pluses on the right-hand side. So under these conditions, will the pressure of NO tend to rise or fall? Well, we've got plus 2x here, so the pressure for nitrogen monoxide should increase, right? We should form more of these products as we get to equilibrium. Now, is it possible to reverse this tendency by adding Cl2? So this is almost a Le Chatelier's principle type concept here. So what they're saying is, well, under these conditions, the concentration of NO should increase because we're shifting to the right. But is there a way that I could sort of mess with this equilibrium such that it would actually shift back to the left? And if we put more Cl2, let's say we just put a ton of Cl2, so increase this pressure of CO2 initially to some really ridiculous high number, well then the effect, according to Le Chatelier's principle, is that will shift this reaction back to the left. So the answer to this, if you said the pressure of if you said the pressure of NO will tend to rise, that's what we said, can that be changed to a tendency to fall by adding Cl2? Yes. And again, the way that we're going to do that is by just adding a ton of Cl2 such that the reaction will have to shift back to the left in order to get to equilibrium. So we've got some concepts here of Le Chatelier's principle. We've also got some concepts of reaction quotients. So if you wanted to calculate a reaction quotient, we could do that. We could talk about that. But I think the easiest way to sort of think about it is initially, so sort of forgetting about this question for a second, initially, this reaction has to shift to the right, to get to equilibrium because I've got a 0 on this side, right? Anytime I've got a 0 initially, we know the reaction has to shift in that direction to get to equilibrium because we've got 0. It can't go the other way, right? We've got 0. So we know it's going to shift to the right. because it's shifting to the right, the concentration of NO will increase. And then if I wanted to reverse that, right, if I wanted to make this concentration of NO decrease, I could do that by putting in a bunch of Cl2. The more Cl2 I put in, the more likely it's going to want to go back to the left. That's Le Chatelier's principle. We're perturbing the system. The system will want to counteract that change. Okay, so now the last part. If you said the tendency can be reversed, calculate the minimum pressure of Cl2 needed to reverse it. Round your answer to 2 sig figs. Okay, so now this part, we need to calculate what the K value is using this equation. So now we've got an equilibrium that we want to sort of set up, and we could write out, for this Kp, I'm using Kp because we've got pressures here. That's going to be the pressure of NO squared times the pressure of Cl2, all divided by the pressure of NoCl squared. Using these coefficients as the exponents. So I'm getting the 2 there, the 2 here, and I'm using pressures because we're given our data in terms of atmospheres. So this makes the most sense. So now we need to figure out what the value of this Kp is, right? We've got some of this information. I've got this atmosphere here. I've got this atmosphere here. This is what we're going to end up solving for. And to solve for the Kp value, let's do that over here. We know that delta G, which is 41,000 joules, is equal to don't forget that, minus 8.314 times the temperature. So we're going to convert that temperature to Kelvin, which is 1332.15. So this is my temperature in Kelvin. Maybe we'll annotate this. So this is Kelvin. This is 8.314, and the units for this R value are in terms of joules. So that's why I've converted my delta G into terms of joules as well. And then natural log of K. And our K is our equilibrium constant for this reaction. So this K here, right, that is equal to that Kp. So to go ahead and solve this, what I would do is I would just divide both sides by this 8.314 times 1,332. And again, I'm just converting, I'm getting this from our degrees Celsius, 1,059 degrees Celsius converted to Kelvin. And if you solve this, you should end up getting K equals 0.02468. So rounding that's 2468. So again, to get, to isolate this, just in case you don't know, you would take e to the power of both sides. So again, divide both sides by minus 8.314 times this 1300. And then e to the power gets rid of the natural log of K. So you should end up with this K value solving this equation for K. So this is our equilibrium constant for this reaction. And this is really related to the value of delta G. We said that this is non-spontaneous. It should favor our reactant side. That's what, this is a really small K value. That's what that tells us. It's sort of the similar information. So now what we want to do is we want to plug that in. 0.02468 is going to equal the pressure of NO, which we know, 1.83, squared, times the pressure of Cl2, all divided by the pressure of NoCl, 2.61 squared. If we solve this for the pressure of Cl2, that's going to tell us basically where that tipping point is. So this is going to tell us what under these conditions, what the pressure of CO2 at equilibrium would be. So if these stayed the same, and then we sort of figured out what pressure of CO2 would get us to equilibrium, that's going to be the sort of tipping point between where it shifts to the right versus where it starts shifting to the left. If I'm above this pressure, then you could think of it as your Q value is too big, right? If you're at this equilibrium pressure, then to get to equilibrium, we're going to shift it back to the left to reform some of this reactant, and that's going to be this reverse process that we're talking about. So going ahead and solving this for PCl2, I ended up with 0.050, I believe. Let me just double check that. Yep, 0.050 atmospheres. So that's the answer that I'm gonna be plugging in here, because that's really that tipping point between where this reaction would continue to shift to the right. So from 0 up until this atmosphere, this will shift to the right to get to equilibrium, but then at this atmosphere we'll be at equilibrium, and if I put more than this atmosphere, then I'm going to be shifting back to the left. That's going to reverse this process that we're talking about. So all the other examples of this problem that I looked at were very similar in terms of the initial situation having one element, or one, not element, but one reactant or product with a 0 atmosphere, helping us figure out which way it's going to shift initially. And then basically it's the same process from there. We need to solve for K, we need to apply that K to our equilibrium constant. We don't really need to worry about the ice table, right? This is just to show us that it's shifting to the right. It's good practice though. And then solving for our pressure, that's the unknown pressure. That's the tipping point pressure. Under that pressure, in this case, it will continue to shift to the right, but above this pressure, we'll shift it back to the left. So hopefully that helps. If there's anything about that explanation that you're confused by, feel free to comment below. Thanks very much.